All right, folks. So let's talk more about graphical models. So before we do, there are two housekeeping items, especially for those of you who are here or watching afterwards. Please fill in the short course survey. It's mainly 4 questions, basically how much you are using and learning from the different course resources that we provide, and also what do you think is sort of one thing good and one thing that can be improved to help your learning. And then we included some background questions about where you're, like which country you're in, so that it's both for this class and also for other large classes, such as, say, document analysis in the next semester. We can better schedule things to help everybody out. So it's been a hard semester with everything the pandemic has to throw at us. So we certainly appreciate that everybody has made it so far. Yeah, we hope to help you through the rest of the semester. And the final exam is 8th of June. Basically, ANU has released its final timetable. It's 8th of June afternoon, Canberra time. So it might be, so starting time maybe 2:40. My memory is a bit hazy anyway. So roughly like last the whole afternoon. We're going to do this on Wattle. If you're auditing and you're curious what the exam is and you want to sort of try or take it, like, of course, whichever you do, your grades, we can tell you your grades, but it won't be released in any way. Yeah, then let us know, because I think on Wattle, auditing students has less rights than the normal students. We can make that happen. We will talk about this and release some resources in the meantime. Basically, we have about 2 weeks of material left, and our last sort of batch of session will be early in week 12, and we'll certainly say meaningful things and give you stuff to prepare for that in week 12. So today we're going to spend time talking about Markov random fields. We talked about Bayesian nets for last workshop session. So we're going to look at undirected graphs. In this session, we look at how it's a conditional independence property of how we can use it to reason about conditional independence. We briefly looked at how directed graphs and undirected graphs relate. And also we start looking at inference in graphical models. So this will be, I think, an informative toy case for both next session, where we talk about the sum product algorithm in general, and also the 2 sessions following that, where we talk about hidden Markov models and other models for sequence data. Right? So Markov random fields, as we hinted last Friday, they're called Markov networks and undirected models. They are defined over a graph with undirected edges, meaning all the connections are symmetric. It doesn't quite specify which node comes first, unlike Bayes nets. So it allows for different conditional independence statements than Bayes nets. So the intuition for this is that in a Bayes net, as we saw, the conditional independence property for the head-head node pattern is subtle because, right, of these descendant relationships. So removing the direction from the edges removes the asymmetry between parent and child nodes. So there's, like, we can call either node at the end of an edge parent or child, and subsequently removes the subtleties associated with the head-head node, as we will see. So here's a definition for separating nodes in undirected graphs. So what's shown here is an undirected graph. Take, for example, the sets of nodes A, B, and C. there can be other nodes other than in these specified sets. If, let's say, A and B are disjoint subsets, and then every pass from any node in A to any node in B passes through or includes at least one node from C, then C is said to be separate A from B in G, right? In other words, this kind of separation in undirected graphs, the conditional independence property, like basically A and B are conditionally independent given C holds for any probability distribution described by this graph. So that looks a lot simpler, right? So let's expand this a little bit and figure out what this means. So more formally, a Markov random field is a set of probability distributions, P of x, such as there exists an undirected graph with disjoint subset of nodes A, B, and C, in which whenever C separates A from B in G, A and B are conditionally independent given C. Basically, the definition of an MRF is defined from this notion of graph separation and directed graphs. So basically, the MRF represents the set of all probability distributions whose conditional dependency statements are precisely those given by graph separation in the manner that we've seen. So what does this definition mean? It means, so we've been reading about sets, but what we're really saying is any node or any pairs of nodes in the two sets we're talking about. So if we have two nodes, xi and xj, that are not connected by an edge, so they are not directly connected and they fall into the sets A and B we talk about. So given all the other nodes in the graph, so it means that XA and XJ must be conditionally independent as all passes between XA and XJ are blocked by those observed nodes. So basically, if we take any two nodes, Xi and J, that are not directly connected, and we assume all the other nodes are known or observed, Xi and Xj must be conditionally independent. Specified in the expression below, basically for the rest of the graph. So here's the picture, xi, xj, there are two nodes, and then there's the rest of the graph. So somehow xi is connected to the rest of the graph. So by the way, we're also, for those of you who have looked at networks or graphs, we're also assuming that this graph is connected, right? There's only one connected component in this undirected graph, because if they are separate anyway, then things will be, right? So if there is a component here and a component there, you can't reach from one to the other, then it is by definition independent, right? So if we assume the graph is one big connected component, then these are all the x's except I and j. So in the literature of graphical models, you will see this set subtraction notation a lot because it's as you can see, it's convenient to represent everything else other than the node that we're looking at. We also saw this notation in Gibbs sampling, which, is basically the same notion. Right. So what this statement says is that it important to consider nodes that are directly connected to each other, meaning what this also says is, in here we say xi and xj are not directly connected to each other, then they're conditionally independent given other nodes, right? If xi and xj are directly, there's an edge between xi and xj, then they are not conditionally independent no matter what other nodes we are conditioning on. Right, so this suggests that directly connected nodes or groups of nodes that are all directly connected to each other are important. As those of you know, if you have taken algorithms, you certainly will know graph theory, you will know. If not, then this is called cliques in graphs. Right, so the derived concept is that cliques is an important concept in Markov random fields, and also we'll see that like there's a algorithm called junction tree algorithm for inference in graphical models, and that's also relying on cliques. So a clique is a subset of nodes such that there exists an edge between all pairs of nodes in this subset. The nodes, in other words, the nodes in a clique are fully connected. So a maximal clique is basically a clique which is not a proper subset of another clique. Or basically, it's the largest subset of nodes that are connected to each other, and we cannot add another node to it that still maintains that it's a clique, right? So here is it's a bit abstract, but here with the example, it's very easy to see, right? So in this particular graph, the 4 nodes have 5 edges in between them, so they are not like the 4 nodes entirely are not a complete clique, right? If we add this edge, then it will be a 4-node clique. Now that it's not, we know that x1 and x2 is a 2-node clique, right? There's 2-node clique are simply like either ends of an edge. That's not news, right? What's more interesting is in here, x2, x3, and x4 is a 3-node clique, right? For 3-node patterns, a complete triangle makes a clique. Undirected triangle, that is, right? And we can easily see that there is like another triangle in this graph, which is x1, x2, and x3. So therefore, x1 and x2 is not a maximal clique, but these 2 triangles, both of them are maximal cliques, right? So a bit of graph theory. And the definition of maximum cliques is now used to factorize an undirected graph, right? So the joint probability of all nodes in an MRF can be written in the following form, right? So recall that in the Bayes network case, we essentially write the joint probability as a product of conditionals. So this is the equation 8.39 is a generalization of that, right? So for MRFs, we write the joint probability as a product of what's called potential functions. So we're not guaranteeing that these potential functions are proper conditional probabilities. So therefore, we need to include a normalization parameter 1 over z in the front. Another note about the next, this section of the textbook is that the literature, although the literature of graphical models is relatively recent, right? I would say it's been, a lot of these key results happened around the turn of the 20th century. So it's roughly 20 years. For example, the sum product algorithm, which we'll talk about, was proposed exactly in 2001, so 20 years ago. There is a fair amount of new terms. So just bear with us with these new terms, right? Some of them, they arise from different conventions or different approaches of trying to do inference. Yeah, so the focus of these lecture are sort of comprehend, for us to comprehend the meanings and motivation of these new terms. We will do a little bit in terms of using them, but we're certainly not going in depth in the graphical model literature. There are entire books written about them, right? So the first term we now encounter is so-called potential functions, right? So again, many of these terms in this and the next session arises from physics. So graphical models is also not an entirely new construct in machine learning, because similar problem has arisen in physics. For example, Markov random fields, the model that inspired it was so-called Ising model in, let's say, formation of crystals. So we will see, we'll explain that in a little bit, right? So here we go. The potential functions are non-negative functions, and the constants ensure that the correct normalization of P of X. In here, we kind of gained not much, except saying that the cliques are defined on maximal cliques X of C, sets of nodes, and they're just non-negative functions. They can be any value. So this gives us a lot of flexibility in defining the joint probabilities. And the normalization factor Z, or it's also called partition function. So here's another thing about these names. For example, potential function are functions, but the partition function is itself a constant. It's a number, not a function. And it's marginalized over all configurations of X, right? So as we kind of hinted in the sampling session, that evaluating the partition function is often hard, especially when there is like cliques of non-trivial size or P of X with many X's, right? So computing the normalization factor Z for the entire graph can be hard, but as we already saw, there's ways to sort of computing P of X without worrying about this partition function. So that's good news in a sense, right? So here we are restating we kind of covered in the last 5-10 minutes or so. So basically, the factorization according to the Maxwell cliques and conditional independence are essentially mutually equivalent properties, right? If a probability distribution factorizes according to the graph, and for any disjoint subsets A, B, and C such that C separates A, B, and C, the conditional independence holds. On the other hand, you can say for a strictly positive probability distribution satisfies the conditional independence, then it also factorizes according to the graph. This is called Hammersley-Clifford theorem, done in the 1990s. So we can see that there is value in strictly positive potential functions. There is also representational convenience that arises with these functions. So here's another new word, right? So if potential functions are strictly positive, again, in graphical models, being strictly positive have preferable modeling value, right? So what this means is that like for unseen configuration of nodes in XC, if we're dealing with words, for example, there are in any given large collection, there may be pairs of words that we haven't seen that appear together, but it doesn't mean that we will never see them, right? We still maintain non-zero probability, like we say that, okay, we should use phi phi of xc slightly greater than 0. Because once we set it to 0, it will be 0 forever. We can't learn the term anymore. So this kind of trick is called smoothing in estimation of probabilities. So one common trick is that if we're doing essential discrete, like counts of discrete values of sets of variables, if there is a configuration we haven't seen, we can reasonably add half a count to it. It is one of many ways of doing smoothing. If you take a natural language course, you will probably learn a number of different tricks for smoothing. They're all reasonable. We won't go into that right now. So because it's strictly positive, the new term we're going to introduce is the energy function E, which is the negative logarithm of the potential function phi. So why do we want this? As you can see that as we usually do in the one common objective is maximize log likelihoods. If we would like to estimate the parameters of a function, then the likelihood, if we write it in this form, then the log of likelihood can be essentially pulled apart into a sum of different terms, right? We know we like sums because they're readily separable when we take the partial derivative with respect to parameters that are inside each term of the sum. So basically, that's why. So once we write a potential function as the exponent of the negative of the energy functions, and again, back to physics, these energy functions have physical meanings, right? So if we're talking about configurations of or rotations of atoms, they correspond to actual physical energy, right? Machine. If we're doing image segmentation, then there is no physical energy involved, but the analogy is still quite pertinent, right? The p of x as a product of these potential functions can be written as essentially 1 over z is the same the exponential of the negative sum of these energy functions. And if we take the log of p of x, we get essentially negative log of z that's separated from these, and then minus a sum of these energy functions. So that's nice, right? So again, in here we can see that z somehow is separated from the e's, and we can perhaps do inference and learning more easily. So another intuition that these expressions allow us to do is that it expresses which configurations of the local cliques are preferred to others. So what it does say is that although the absolute value of phi can be anything, but the relative value of phi's for different values of x of c are important, right? So when we do inference, we sometimes wanted to reason about which configuration of x is more likely, such as image segmentation, as we will see. And then the global configurations with relative high probability, or basically the more likely configurations globally, are those with a good balance in satisfying the possibly conflicting influences of different clique potential terms phi of xc. Okay, to ground what we just said, which is a mouthful, to a concrete example to help us establish, what do you mean for these potential functions? Let's look at an example as presented in a book, right? So here in this toy example of image segmentation under noise, or denoising a noisy image. So in here we assume The noise-free image, which the authors drew, Bishop and his colleagues drew, is, let's say, a binary image. The pixels are +1 and -1. Let's say the blues are +1, the foreground, and then the yellows in the background are -1. So we corrupt this image by introducing some noise, right? By randomly flip the sign of some pixels with a small probability. The goal is to recover the original image as much as possible. So we already saw an exactly the same application using autoencoders, right? So if we have lots of image pairs that are noisy and like clean, we can essentially train a neural network to try and come up with the cleaner image given the noisy image, right? In this particular problem, we are going to assume that the model is known, but we're just going to, we're not going to learn anything. We're just going to do inference by trying to guess what the cleaner image is. So here is the picture with 10% of the pixel flipped. As you can see, it's quite kind of messy. And this is a picture of the undirected graphical model representing this image denoising application, right? So for each pixel, so the Ys are the observed or noisy pixels, like the picture like above, and the X's are the unobserved. So they're unobserved, so we gray out the clean image, but they are supposedly the clean pixels, right? The problem is given the Ys, we wanted to infer the X's. Furthermore, the dependency situation of X and Y's are that given X, the Y's are independent of all the other variables. This is reasonable because essentially we said in the last page, right? Probability of yi equals to xi given xi, right, is 90%. We said we flip the pixel, 10% of the pixels, right? This is what this dependency edge means. And then we also see that, the xi's are connected to its, let's say, four neighboring pixels. Intuitive for image, the image tend to be smooth. They don't randomly vary from pixel to pixel. So it's reasonable to expect that the information from neighboring pixels play a role in denoising the image, right? And here's the model, right? Or specification of the energy function. So in this particular case, notice that this energy function is directly specified as this sum of energy functions in the term here. Right? We're not spelling out each of the cliques. So what this says, also notice in this graph, right, the cliques, the maximum cliques, are these the x's and the corresponding y's, and also the x's with its neighbors, right? So here is the energy of sum of the edge potentials. So we can say that the energy function that's been designed has three terms. The first term is h times individual x's, right? To encode the intuition that a pixel is probably more likely to be background than foreground, or the other way around, depending on the image being segmented, right? And the second term is basically xi times xj multiplied by a scalar parameter beta encodes the intuition that the neighboring pixels tend to be the same. Right, so if neighboring pixels tend not to be the same, then this sign should be flipped, but here it says basically neighboring pixels tend to be the same. And similarly, in here, it has the cliques are xi and yi's. So it's multiplied by a different parameter, eta. It says the pixel and the corresponding corrupted pixel here tend to be the same. So that's all the intuitions that we can encode. And as you can see, these parameters, beta and eta and h, trades off the forces across these different intuitions, right? And let's just plug this energy function back to the joint probability term expression. Just taken from 2 pages ago, the probability of this whole sets of nodes, x and y's, are 1 over z. We don't know what z is and don't care right now. X of negative of the energy. So for the so what this says is lower energy. Again, this has a meaning in physics. So lower energy leads to like higher joint probability p, x, and y. Let's verify that, right? So if xi, xj, the product of the two is 1, then the energy term is lower by if beta is a positive number, right? Similarly, if xi and yi, the product of these two is 1, then the energy is also lower. If the xi and yi are different, then energy goes higher. So higher energy in here means a penalty. So because we preferred, so the ideal case, right, so to, let's say, minimize energy between the x and y's, since we observe y, the ideal like configuration that just optimized this term will be all the x's are the same with the y's, right? That will A, not do any denoising, and B, it will incur a lot of the x and its neighboring x's to be different, and thus penalizing the middle term, right? So that's bad. So the other option, extreme, will be I minimize the energy of the middle term. Basically, all the x's are the same. Then the picture will not have any contain any meaningful information. Then like for example, every pixel will be labeled foreground or background, and this last term will be penalized a lot. So this is what we're talking about in what this statement means, right? So we need to strike a balance between, in that case, good balance in the conflicting influences of the clique potentials. In this case, basically the like preferring neighboring pixels to be the same, and also preferring the noisy pixel and the clean pixel to be the same, right? So now, given this design of the model, let's do inference. In here, I say inference because what we're doing is we're assuming that someone has given us the betas and gammas. And here we assume ignore prior h is 0. So that term is practically gone in here. And we're just trading off betas and gammas. And someone told us beta should be counted as 1 share and etas, etas, not gammas. So in the eta should be roughly twice and a little bit more, 2.1 of the weight of betas. As you can see, an MRF can be parameterized quite simply. In here, just 2 parameters. In reality, how complex your MRF model is depend on your domain and what other intuition you might have about the problem. And also the diversity of your training data set, so to speak. In here, there's no training, and we're just denoising a simple handwritten picture, and we assume these are given, right? So given these beta and gamma, So here is an approach that greedily denoises, tries to denoise each pixel, right? And here are the results, right? Starting from the noisy, very noisy image that we saw, we can, let's say, initialize all xi's and yi's to be the same. And then we take one node and evaluate the total energy for both possible states, right? Keeping all the other variables fixed. So basically, we try to flip one pixel and see if it improves or lowers the total energy. So then we set xj to the state having the lower energy. So here's the intuition, right? Because the x, so I'm just going to draw an xi and yi. And here are, let's say, so the weight on this edge is gamma, eta, and the weights on the edges, so to the other pixels is beta. We know that eta is roughly twice beta and a little more, right? So, and there are 4 neighboring pixels. So, for example, if you were greedily trying to find an x that you can flip to improve the energy term, you can, for example, if an x is different from all of its neighbors, or at least 3 of the neighbors, if you flip this x, you are going to improve the energy function, right? If x is sort of the same with the neighbors and it's the same with the yi, if you flip it, you will not improve the energy function, right? Okay, so you basically go around this image looking for x's to flip. As you can see that your label for the x's is influenced, or it also influences the label on the neighboring pixels, right? So in the worst case, these could go in circles, right? I decide to flip xi, but then in a few rounds downstream, I'm flipping its neighbors too, then I need to flip xi back. So you, let's say we're not gonna worry about this for this particular algorithm, which is called ICM. So this is how, I think it's also one of the first algorithms that physicists came across to, to solve what's called the Ising model. Basically, what are the rotations or configurations of atoms when the atoms closely interact with each other, right? So, and then we basically go around until stopping criteria is satisfied. Basically, if we go through the whole image, no node would change its label, then we stop. Or if we go through like, or a slightly lazier, but easier to evaluate stopping criteria is that, for the last 1,000 pixels I have examined, I have not been able to flip any node. Maybe it's time to stop. So if we do this local greedy search or greedy node flipping algorithm, we get back this image. You can see it's still kind of noisy, but it's a lot cleaner than the noisy image that we started with. So it's doing something good, right? Turns out that we can also find the global minimum of this particular energy function using an approach called graph cut. It's invented by 2 Cornell researchers, Rami Zabin and Bromerkov, in 2004, I believe. We're not going to cover how this is done, but for those of you who are interested in image segmentation, it's a very nice algorithm. Well, actually, computer vision might have covered it. So is there any questions so far about what graphical model and its inference, or MRFs and its inference means? Okay, if not, we're going to move on. we're roughly halfway through like this written material that we plan to go through. So the next section has a fair bit of notations, and hopefully we will like convey the intuition behind these notations. And then afterwards, you can read the book again to sort of reinforce your own intuition, so to speak. So we're going to take a look at the relationship between directed versus undirected graphs. And we do this first for chains and then for general graphs. And then we will look at how do we do inference on undirected chain and tree graphs. So recall a chain where there's a series of nodes where the lower number nodes pointing to its next node and all the arrows are the same direction. We know that the joint probability of these n nodes factorizes according to this. Basically, every node conditions on its ancestor or its parent, immediate parent node. And the nodes of higher numbers are conditionally independent of all the earlier nodes given the immediate preceding node, right? So this is simple. In fact, we do this in Markov chain Monte Carlo. This is a Markov chain. We do this in Markov chain Monte Carlo. We do this in sequence reasoning and so on. So this is a simple but very powerful and frequently used graphical model. Like you do this for inferring properties in text, whether it's named entities or parts of speech. You do this for decoding speech or speech recognition. You do this for biological sequences and so on. It's so useful. So, and we would argue an equivalent undirected graph representation is simply the same chain removing all the arrows, right? According to what we defined a few pages ago, the joint probability in this undirected chain graph is written as a phi, a set of potential product of the set of potential functions over maximal cliques. In here, it's simply like the nodes. These are all two cliques, the nodes at either end of each edge, right? So it's written as that. Because we know the expression 8.44 is properly normalized, we can now readily map out the content of each potential term and the z, right? So we can say that phi of 1, 2 involves the prior of x1 plus the condition of x2 and x1. So basically the joint of x2 and x1. Every subsequent potential term is the conditional probability of the node given the node immediately before it, right? So we can simply map out these two in a like sort of the mapping of these is one-to-one fashion. Moreover, it's very nice to see that in this case, the partition function is z is not an unwieldy beast, it's just 1. So great. Right, by the way, for the image denoising case, in this particular case, we didn't need to reason about this normalizing factor z because we're just concerned with flipping the status, right? Okay. So that was one example of converting or finding out the equivalence relationship between directed and undirected graphs. The more general way of reasoning about like try and see what is the closest undirected graph for a given directed graph. The name for that, again, it's a new name, but it's just inspired by this whole set of terminology about a node and its parent node and so on. It's called moralisation. Right. I would say these terms are sort of, they have a different connotation right now in like in this society. Like you can say, it's called moralisation because we are given a base net. We create the cliques for Markov random field by adding undirected edges between all pairs of parents for each node in the graph, right? It's called moralisation because we are so-called marrying the parents, right? Take this like this name with plenty of tongue-in-cheek, right? I think in this society, marrying, right, is sort of it's not as it's not certainly not a necessary process in civil society, but we're just say tongue-in-cheek saying we're doing this to the parent nodes. And for example, the process of moralization for this simple four node graph with like a three head and head pattern is we connect all of these parents, right? So for basically if two nodes are co-parent of something else, we connect them. And then we remove the edges. Then we get this node. So for this particular example, moralization actually gives us a fully connected graph, right? So for a four-node graph, this new undirected graph has 6 edges, making it fully connected. So it kind of, we know that the absence of an edge in Bayes network represents probabilistic structure, but the structure is completely gone here. So you may say, what is the point of this, right? So let me just say that this is a warning that the directed graph and undirected graph, they are different languages for expressing conditional independence. But the way you can use them is, one example of using them is as follows. This is, I don't think the book, Bishop book, gives a constructive example. It just says, well, you are warned if you moralize or turn the Bayes network into an MRF, you're going to land up with a likely different conditional distribution or a joint distribution expression. On the other hand, this is, for example, this MRF with no dependency structure, independence structure constraint is sort of a strictly larger class than the Bayes network with special conditional independence structures, right? So when we say larger class, it's basically for all the possible parameters that these conditional probabilities can have, we can certainly express them in a fully connected graph, not the other way around. So here's a use of this moralization step, right? We can actually use it to reason about deseparation as well. So this is outside of the book. If you're interested, you can read like the source of this example. What it means is basically the first step is we wanted to reason whether A and B are conditionally independent given two other nodes, D and F. If this is a fragment that exists in a larger graph, we basically pick all of these nodes in question and then take a subgraph that include these nodes and their ancestors, meaning it's ancestors, not parents. Meaning if there are other nodes, let's say dangling off D and F, we wouldn't care, right? We drop them. And if there are, say, nodes pointing to A and B, we also wouldn't, we would actually include them, right? So in here, okay, this is the ancestral graph that we end up with and we reason with. We moralize this graph by looking at each node and then connecting their common parents. In this case, we only need to moralize A and B because they are co-parents of C. And then we disorient by simply delete all of the arrows of the edges. We end up with this graph, right? And then if we now we read the question more closely. We say that we wanted to reason about A and B, right? Whether A and B are conditionally independent given D and F, right? So we delete or we hide the nodes being conditioned on. In this case, we hide this to get that. And then we simply see if A and B are still connected in this graph. In this case, it is. So therefore, A and B are not conditionally independent given D and F. Right. So how does this correspond to our other language in D-separation, right? So we basically, in the book, we learned about, if there is a head-head pattern between the nodes we wonder about, we look at whether their common children node or any descendants of this children node is observed. If they are, then A and B are actually dependent, right? So this is true, right? So it's the descendants of the common children node C that's observed, right? So A and B are not conditionally independent. So we can also ask if actually none of C, D, and F are observed, is A and B conditionally independent, right? So this is what the next example says. So, so the emphasis on nodes being unobserved in a Bishop book might seem somewhat sort of unusual. The way the term, like the language that's used elsewhere, for example, are A and B marginally independent, right? Without other nodes being observed, which means the same thing, right? So we know from the D-separation that we learned they should be marginally independent if C and D and F are all unobserved. So now we draw the ancestry graph. Now we're only concerned about A and B. So we can drop the CDF part, right? We moralize, there's nothing to connect, right? No parents, no co-parents. We don't disorient, there's no edges, and we delete the nodes observed. There's nothing, no other nodes observed, so A and B are just still disconnected. So indeed, it's the same conclusion we got as using what we learned last time. So A and B are just conditional, or they are independent of each other if the other nodes are unobserved. So this is how we can use moralization. So there's a bit more terminology introduced by the book. It says graph is the D-map, dependency map of a distribution if every conditional independent statement satisfied by the distribution is reflected in the graph. Right. A graph is an independence map of a distribution if every conditional dependency implied by the graph is satisfied in the distribution. Right. So these two definitions, like the graph is a necessary condition for to represent the terms in the joint distribution, and in here the graph is a sufficient condition that of the conditional independent statement expressed in the distribution. And of course, a P-map is both, like, basically establish if a graph is a P-map of the distribution, then they are like sort of necessary and sufficient conditions of each other. Why are we bothering with this? It is because of the following view. I remember someone, Noel, asked, essentially, why are we bothering with this filtering terminology about like conditional independence in distributions and graphs? So maybe this one will help, right? So if we have a set of distributions P, basically sort of P of X as a vector, and X vector equals X1 through some fixed dimension X. So this is for all joint distribution of D variables. And the domains of the D variables are fixed. They are, for example, all binary, they're continuous, or some fixed mix of binary, discrete, or continuous. The red circle represents all possible joint distributions of these sets of variables. And the green circle represents the ones that are representable by any base net, any D node directed acyclic graphs over all parameterizations. The set is pretty big, right? And then the blue node represents all possible MRFs over the same set of nodes. Right. The point of this picture is to say that although there are equivalence conditional independence relationships that we can derive from them, for example, using this, the process moralisation, the subsets of conditional or joint distributions of variables, the base net and MRF represents are different. There are intersections, there are also set differences and stuff that they cannot represent. All right, here's an example for each. As you can guess, what's different, most different between these two sets are actually these head-head node patterns, right? As we saw, if we moralize this graph, this into undirected, it becomes fully connected, right? So this particular head-head pattern is in a set that's representable by Bayes networks, but not by the by Markov random fields. And one constraint of a Bayes network is that it wants, right, it needs to be a directed graph without cycles. But there is no say about MRFs cannot have cycles, right? This little network down here in the bottom, we can think of this as the pixel segmentation or denoising graph, right? Where each pixel is connected to its neighboring pixels, and of course it has cycles. So this kind of joint probability distribution can be represented with a Markov random field, but not by a Bayes network. Okay. Suffices to know that they are somewhat different. Although the book also makes this nice point about for the purpose of inference and learning and reasoning about graphical models, it is common to convert Bayes net to a, okay, I'm just gonna convert a Bayes net to an MRF, but it's kind of uncommon to try and find the equivalent Bayes net to an for an MRF. Because there are, partly because of the available inference algorithms. As we will see, factor graphs and some product algorithms, it works for MRFs and also works for Bayes nets. But the specialized Bayes network inference algorithm don't work for all MRFs. Okay, to sum up, the directed and undirected graphical models, they specify the relationship between the graphical objects and conditional independence statements satisfied by the distribution And the conditional independence statements are related to concepts of separation between variables in the graph. Right, so for Bayes nets, the separation for MRFs is essentially separation of subsets of nodes. The simplified algebraic structure is related to what's called local pieces of graphs. So it's cliques in MRFs. In Bayes nets, it's a different set of objects. Basically, it's the parent-child relationship in Bayes networks. So for those of you who have looked at graph theory terminology, so these are all essentially local structures, right? Like for examples of non-local, right? Non-local graph properties, or let's say measures, don't quite count, right? So for example, like path length. We care about whether two nodes are separated. We don't care if once they are separated, how many hops you need to run before you sort of reach another node from one node, right? So like connected components, we assume the graph is connected. If they are not connected, then the different parts are like independent in terms of joint distribution, right? Okay. So we also said with an example, the sets of probability distributions that can be represented between the two sets of graphs are different. Right. Markov random fields, the price to pay, again, there's no free lunch in modeling. The price to pay for having simpler reasoning of conditional independence is the introduction of this normalization constant that couples all of the factors. We need to like compute a product of all the factors or potentials and sum them up. But Bayes network does not. Right. The local pieces of Bayes net are probability distributions themselves. This is like the last point is the reason for the middle point, right? In MRFs, they need only to be non-negative functions for like which is both good and bad. Right? And they may not have a range between 0 and 1, and they may not be probabilities. By the way, for Bayes nets, the range is only between 0 and 1 when the variables are discrete. When they are continuous variables, as you can see, the probability density can have arbitrary values as long as they integrate to 1. Right? All right. So we're going to look at inference next. Is there any questions so far? People are happy. We're gonna move on. So we already saw an example inference with the image denoising model. In here, we're going to look at a more general case. In other words, so we clamp some of the nodes to observed values. We wanted to compute the posterior distribution or like of other nodes or one of a more subsets of other nodes conditioned on them, right? So in the image denoising case, what we ideally wanted to compute is probability of all the X nodes conditioned on all the Y nodes, right? But in fact, what we were computing, like in the iterative algorithm, was actually an argmax. Basically, we don't actually compute the exact probability value. We wanted to find maximum like probability configuration of the x's given the y's, right? So the general ideas here is, since we have a graph, we would like to explore the structure for efficiency and also to provide intuitions about why we end up with a probability like that or argmax like that. As we said, the local structures in the graph is the key towards achieving some of these representational efficiency and succinctness. So we wanted to explore the mathematical expressions of local structures influence each other. And we focus on exact inference in this class. Basically, we focus on graph structures where we can compute the exact probability or the exact argmax. This class, I think the previous years have a section on approximate inference, and this year we don't have time for this. So if you're interested, you should look at chapter 10. Right, I would say we mainly talk about inference, but it's an essential step in learning. So roughly speaking, so this is the E step, right, in the EM algorithm that you already saw. So as you saw that the E step in Gaussian mixture models is essentially computing something like this. It's P of Z given X in the notation there. And after we compute that, because the distribution were Gaussian, estimating the parameters were easy. We just directly import the formulas we learned from maximum likelihood, right? So yeah, we were talking about Gaussian mixture models. Let's just look at exactly the same graphical model and even a simpler one. Here we assume X and Y are discrete and we're looking at essentially 2D probability table. How do we do inference in this? Right. We may ask, right, so here are 3 instances of this probability model. It's also a chain, by the way, so because of the nice things we said about chains, if we convert these graphical models to undirected, they're all the same. Note here that it is like, basically we can flip the edge, right? So we can ask what probability of Y is, marginal probability of Y is. According to Bayes' rule, we simply break it apart, especially for this A graph. We break it apart using Bayes' rule and then like marginalize some of the value, different values of X. Right. And we can ask what the value of X given Y is, because this is quite a common graph, right? We said that the children nodes are descending nodes are what's observed, and the latent nodes are what we thought as driving the observations, but we don't observe them. So think of this as just one slice of the image denoising problem, right? And we can compute P of X given Y again using some product rule, right? So you say, oh, then that's easy. How do we generalize this to larger graphs? Right. So also recall that here is one step towards doing this, right? So we're going to only look at chains in some detail right now, and then the next session is going to be entirely devoted to this topic for general graphs. Right. So for chains, we noticed that for the undirected version, we factorize the germ probability as follows. It's basically a bunch of pairwise potential functions, right? And our goals may be to compute the marginals of some node in the middle. In here, let's just say xn is in the middle, and it's connected to xn minus 1, xn plus 1, right? Let's say. So we can say we do this brute force, right? We already saw that although this chain of potential is long, it's the same expression as conditional pairwise conditional probabilities. We can say we write out this whole chain and then we just sum up over the variables that we don't care about, right? If each of these variables have up to k states, oh, this summation is going to be exponential in n, or in the dimensionality of this chain, right? So that's not desirable, right? We can do this, but it's kind of painful. But so far, we have not used this factorization property of this distribution. So how do we use it then? We notice that, for example, if we want the margin of this node in the middle, we don't need, also, there is a typo, I think. Xn should be at the end. We can see, well, we don't need the last node, x of big N, right? So what if instead of marginalize xn in this big joint, we can pick out, we also know that the x of big N is only in the last potential term, right? And this term is essentially probability of xn given, or big N given x big N minus 1. And xn is not anywhere else. So we can essentially move this summation term of xn to just this last potential term, right? And we can, so there's a bunch of phi's in front, and we can still sum over all these things from x1 to xn minus 1 and xn plus 1 all the way to x big N minus 1. So all the stuff in the front don't change, and we can just pull this summation of x big N into the last term. And we know this, for this particular one, it's just a summation of k different terms, because that's the state space of xn. And now we have sort of made one step of progress towards simplifying this giant messy sum, right? So let's build on this, right? I would say that, so here is the perspective of, it's a spoiler, but so dynamic programming, for those of you who have taken intro to CS or operations research or electrical engineering, portions of electrical engineering, information theory, and so on, you would have seen this algorithm elsewhere. So this is an algorithm that's so useful that it keeps reappearing in different scenarios as in different names, right? So essentially what I say that the rest of this session and next session are dedicated to dynamic programming and its different relations in graphical model inference. So if you have used this elsewhere, you will feel this is familiar. I would say for each new application that I've seen so far, it still takes considerable amount for me amount of brain power for me to contextualize it for different things, right? So if you have used this in bin packing or warehouse problem, or actually like what's called knapsack problem, in operations research, we will look at Viterbi decoding, like let's say DNA sequence alignment. These are just the same algorithm used in different places. It's so useful. And what we cover is readily, right? So we'll cover this, and we'll cover the version that's directly usable for this one as well. For the knapsack, it's once you learn it once, it's a small step to generalize to others applications such as knapsack. Okay, so here we go. This is exactly what we're doing. So we essentially try and distribute these summation terms to basically for the second half of this big sum. basically, as we can see, there are intuitively two parts of this giant sum. One is before the variable we care about, x1 to xn minus 1, or the other part is the second part where it's after the variable we care about. So for the second part, we move because like these the later variables are only constrained to appear in the later potential functions. After we done this, we did this for we sum marginalize out the x big N. We can do the same thing with xn minus 1 and so on. So we do this, we move the summation sign to the last part where they appear. And then we perform the sum after we performed subsequent sums. And the corresponding variable will disappear again from the expression. So that's nice. So we call this whole part of the result of summation mu of beta indexed by xn. So it indicates, right? So the terminology of alpha and beta here just sort of indicates whether it's before or after the variable in question, and the variable in question is xn. And the partition function or normalization remains the same, right? Similarly, for the front part, as we can see that because the graph is undirected, right? The way we can marginalize our x big N, we can apply the same trick to marginalize x1 by only considering the first potential sum, right? So we do this, we sum out x1, and then we marginalize our x2, do exactly the same thing until we get to xn minus 1, or 5, the potential terms of contains n minus 1, we can marginalize that out. And then we note that the term xn appears here and here, so xn is not going to be marginalized out because when we compute this, this is a sort of a 1 by k vector that we wish to retain. For each value of xn, we want a value. Okay, we do this. And notice we have included all of the potential terms phi in in either of these summations. So at the end, the expression of the marginal probability of xn is simply the same potential function times what's called whichever we call the forward or backward message, basically the mu alpha term times the mu beta term. And we can see that the complexity of performing each of these sums is k squared. It's not k because what we're doing is so these phi terms, let's say phi of 1, 2 is a table, right? So let's say we have rows corresponding to x1, columns corresponding to x2. Right, so this sum corresponds, so, and there's k square numbers in here, entries. We sum over x1, meaning performing actually column sums. What we're doing is we're doing column sums of this table. Right, and we're doing so for every single potential term. Therefore, there's roughly n of them. So the complexity of doing so is n times k squared. Moreover, we can have, so we've solved this case. And going from O of like exponential in k to like k squared is pretty good in terms of computation. Moreover, we can also express this whole terminology more succinctly by recursively define these alpha and beta messages or functions, right? So these, so-called messages, as we will use next time, is simply functions with part of the potential term marginalized out. So we first, in order to compute the messages for xn, we need to derive this from the messages that's sort of centered on the nodes xn plus 1 in the backwards direction, and so on and so forth until we get like, oh, right, where's my pen? The messages mu of beta of xn, right, which is that term at the end. So here is how, like, essentially we write out the recursive evaluation of these messages, right? For the forward messages, what we do is the mu of alpha x2. So x2 is the node that we keep. So I correct myself. So the notation here essentially, the last message is mu of beta xn minus 1, not xn. Or if we treat mu of beta xm as 1, that also works too. So, right. So this is the first message, and then we recursively define this message as essentially the last the message on the previous node times the potential function with the previous node marginalized out. Same thing goes with the backward messages mu of beta. All right. So you can say that, oh, we covered how to compute the marginal of one node in a chain. That's kind of limited, right? If I'm doing image denoising, I want all the nodes. How do we do this? So if we have a chain, we can essentially compute and store. So we're trading off computation with memory, a little bit of memory here. So we can see that in a chain, there is one of these messages for mu of alpha for every node. There's also one of these messages, mu of beta, for every single node, right? So we can just compute these two sets of messages, mu of alpha and mu of beta for all nodes, and store them. And then we can basically combine the corresponding pair of them to compute all marginals on all nodes. So that's useful. So we repeat the above, right? The naive strategy will be repeating this computation n times. But if we store all intermediate messages, I think, right, it's O times nk squared, O of nk squared, right? So, and also, what do you say about observed nodes, right? Because that's where we started saying the generic, say, P of x little n condition on x1 and x2, right? So in that case, we can save some summing over, right? We no longer need to sum over the term, right? So instead of sum over x1 phi of x1 x2, we simply plug in phi of x1 equals something, and then x2, right? And if we compute joint probabilities that are only like for two connected nodes, what we do is we use the same messages, right, up to node n-1 and up to xn in the other direction, and then insert the potential term in here. In here, we just end up with a k by k table. And the computational complexity is the same. So we covered a recipe that pretty much covers most of the questions that we want to ask for chain graphs. So that's nice. So here's a word for tree-shaped graphical models. It turns out, so first of all, what is the tree, right? So an undirected tree is basically there is one and only one path between any pair of nodes. And there's no loops in the tree. And you say, wait. So we know that in a tree, there's a terminology of every node has only one parent. Where does that come from? And where is the root of the tree, and so on. So I actually argue that, so there's a simple result in graphs and algorithms. If you have seen them, it's basically for an undirected graph, any node can be the root. Right. I use this loose analogy, like if we take this graph A as an example, you can figuratively, basically the graph layout is, you can arbitrarily rotate the graph layout. If I want a tree where the root is the top, I just take any node and then shake this graph with all the nodes that are falling under it. Imagine there is gravity on each node. Then you can see that it's like if we take any node, it's a valid tree, right? Oh, for directed graph, there's a single node called the root, and then yeah, right. So another corollary is that moralisation on directed trees will not add links, right? So we can simply just delete all the we can delete all the edges, all the arrows in a directed tree, and then it will turn into an undirected tree. So inference on trees can be done similarly. So this claim comes from the fact that if we would like to condition, like compute the marginals of any node, for example, this node, we can treat it as a root, and then we can basically perform the sum that we just performed from upwards from the leaf nodes, right? So, for example, in this second graph, if we want the marginal of this node, right, we, again, figuratively turn this into an undirected graph, take this node and shake it, like make all the other nodes dangle next to it, and then we start marginalization from these root nodes, and then work backwards. So the only difference here is from the chain graph to this is that there are nodes with two children nodes, right? Then we need to deal with basically two message terms, right? Two of these mu alpha or mu beta terms that comes together in a node. And we'll, so let's just say that for trees, we can also efficiently do inference in pretty much quadratic time, right? So the difference, so this the graph in picture C is somewhat different. It's called a directed polytree, right? As we can see, if we moralize this, it does add an edge. So the claim here, again, bear with us until next time, is that the sum product algorithm still applies to the directed polytree. So the directed polytree is sort of a class of nodes, graphs that are not strictly trees, but still efficient inference algorithms are available. Okay. So this is all we have to say today. We looked at Markov random fields. We looked at what its conditional independence look like and how to factor what are the ways to express the joint probabilities. We looked at its relation to directed graphs and example inference on chains in detail, and we claim that it works on trees too. Is there any questions? No. Let me check the chat log. Seems no. Okay, I hope you're all happy and find this content easy. I would say some product algorithm from my view is a bit abstract, right? So there is a little bit of distance between what you see in the textbook discussion and also what you can code, right? So in coding, you sort of need mentally sort of one more layer of abstraction in how you represent the different values of nodes. And then what you're exactly summing over, right? Exactly this probability table notation that we were talking about earlier. So other than that, it's really not that difficult. So if people are happy, I'm going to stop the recording and pause for a few minutes for questions if people have any.